Thanks. OK, so today I'm going to talk about, well, I should probably reverse the order of the words in my talk. It should be circuit and proof complexity, but that's OK. So I study computational complexity theory. You'll see what I mean. You'll see what I mean. So I study computational complexity theory. So what's the basic problem that we kind of consider? So the most basic problem that we consider is you're given a Boolean function, okay? So something that maps the cube to just, a bit, 0 or 1. And the question is just, how hard is it to compute f in some specified computational model? And by hard, I mean like how much of some computational resource do we need to consume? So when I say hard, think how much of a resource, like time or space, like amount of memory in a computer or something like that. So how hard is it to compute f in computation model M? Okay. So obviously a lot goes into this part of this question. Like, what do I mean by a computational model? And there's lots of different examples that occur in the literature. I mean, a pretty common one that maybe some people at least heard of is like a Turing machine, or like a RAM machine is a good model of something on the computer, or like a finite automata. So for today, I'm going to fix completely to one example, which is my favorite, and it's just the model of Boolean circuits. Okay. So if you want to see what a Boolean circuit is, here's one. So the idea is at the bottom, we're going to have some input variables. So in this case, we have two, x and y. They take Boolean values. And then the interior of the circuit is basically the circuit computes this Boolean function by repeatedly composing other functions. Okay? So in this case, the functions that we're going to compose are and, like just take the and of your 2 bits, or take the or of the 2 bits, or not, which just negates a single bit. Okay? So you can, I guess so does anybody know what function this is computing? Can anybody tell? See, circuit complexity is hard. This is like proof. Any guesses? No? OK, well, I only have 15 minutes, so I'll tell you. So it's just the sum mod 2, right? So it outputs 1 if exactly one of its inputs are 1. See? Does that make sense? Cool. OK, cool. Or really, it should be the negation of the sum mod 2. But whatever. So the size of the circuit is going to be defined to be the number of gates, so the number of different gates that we're going to use. And you should think of this as being like a measure of complexity of the function. Okay? And in general, this is what we're kind of interested in studying. So find good examples of functions which require really large circuits to compute. That would be an example of like a hard function, right? And the parity is an example of like an easy function. It's computed by a very small circuit. And you can generalize this construction and get a pretty small circuit on average. So what's kind of a motivation for studying this kind of problem? Well, let me give you a more general example, like a more generic example that occurs in the literature. Yeah? It does. Oh, good question. It doesn't have to be like a tree. So the one that I drew here is like a tree. But in general, you can fan out these gates and reuse your computations as many times as you like. OK. So let me just give you a definition of a function, one Boolean function that we would like to understand. OK. So it's defined with 2 parameters, n and k. And it's going to map. So you're going to get a list of bits of length n choose 2. And you should think of this list of bits as encoding a graph on n vertices. OK? So a graph just by listing its edges, right? And now this function, CLI n sub k, or clique of nk, this is going to output 1 if and only if the graph that's encoded by x has a complete subgraph with k vertices. Okay? Complete means all the edges are there. So between every pair of vertices on this subset of k, there's an edge. So, maybe like this is your graph, and this would be an example of a complete subgraph on 3 vertices, right? Okay, cool. So, this is not necessarily one Boolean function. It's like a family of Boolean functions for each choice of n and k. This is usually the situation that we're interested in studying, because we want to study like the asymptotics of what the smallest circuit, depending on n and k, is, right? So why is this function particularly interesting? Well, here's a fact.
When you say one function, you mean
Sorry?
You mean at least one or exactly one?
At least one. Just, yeah. Yeah. So here's a fact about this function. Say, so if any Boolean circuit for CLI and k requires size at least, let's say like n to the d of n. And I don't really care what d of n is as long as it eventually diverges, like it grows with n to infinity. So this is like super polynomial growth rate. Well, then p is not equal to np.
What about k?
Sorry? Oh, well, yeah, k is a parameter. For this kind of growth rate, just think of k as being anything that depends on n. So I don't know, you could take k to be any function of n. Going to infinity with n, yeah. If k is constant, then it's not hard to produce small circuits. Okay. So this is basically the motivation for studying these things. This is like arguably the central problem in theoretical computer science, right? It's one of the Clay Prize problems. So, okay, so you can ask what kind of progress have we made on this so far? And the best lower bound that we have is 5n, minus actually a little o of n factor. And this is after years and years of work. So yeah, there's a big gap between the best lower bound and what we expect to be true. There's no doubt about that. Okay. Okay, so what's going on here? Why is this? Why are we stuck at 5n? There's a long. There's a lot of answers to this, and there's many ways in which the techniques that we use to get this 5n lower bound, like provably in many cases can't give superlinear lower bounds. And in fact, for the general case, we just have literally no idea on how to prove superlinear lower bounds. Let me just, to try and explain where some of the difficulty is, I'm going to talk about some restricted models. Okay? And in more restricted models of Boolean circuits, we can make quite a bit more progress. And I actually think that like some of this sort of hardness becomes like illuminating once you look at them. Okay? So how could we restrict a model of Boolean circuits? There's a couple of natural ways. One is to so for example, we could restrict the topology of the underlying graph. We could enforce, the underlying graph to be a tree. Okay? So, or you could make, any kind of your favorite kind of restriction on the graph, and somehow this should restrict information flow through the circuit. But that's actually not the one I'm going to focus on. What I'm going to focus on now is instead we could restrict the set of functions you're allowed to use when you're doing the computation. Okay? So when I say a gate, I just mean what functions you're allowed to use inside the circuit. Okay? So with that, let me just give you a definition. The particular restriction I'm going to look at today is going to be the monotone restriction. And you can imagine that what that means is I'm just going to remove the not gates. I'm not going to let you use not gates. So it's called monotone because and or are both monotone functions. If I flip a bit from 0 to 1, the output can't flip from 1 to 0. Okay? So So here's a definition which everyone knows, but I'll just write it down for posterity. So f is monotone if whenever x is less than y, f of x is less than f of y. Okay, and this is a string of bits. So think of this as inequalities being bitwise. Okay, and we'll say the circuit is monotone if it has no NOT gates. Okay, so only and or.
That's the same. The gate could have more than two variables or not?
It could have many variables. Yeah.
Still reducible to and
Yeah. Oh, absolutely. Yeah. Every monotone function is computable by a monotone circuit. Yeah. That's and or is like a complete basis for monotone functions. Okay. Well, unlike in the non-monotone case, where our best lower bounds are kind of embarrassing, in the monotone case, we actually have very strong lower bounds. Okay. So here's a theorem due to Razborov. Okay. Any monotone circuit for this clique function. And I'm going to put a mild restriction on what k to be. So k is going to be some power of n. Think of epsilon as just being like a small constant, like 1 over 100 or something. Requires size at least n to the k. Maybe like c times k for some constant c. Okay. So I mean, if I choose k to be like n to the epsilon, this is an exponential lower bound, or like a weakly exponential lower bound, right? So this is exactly the kind of growth rate that you would expect in the non-monotone case, right? Okay, so it's really natural to ask then, like, what's so special about monotone circuits that allows us to break through this barrier that we're facing, right? And it's not fully understood, but it's somewhat understood, and that's what I'm going to talk about. Okay, so maybe a first question.
sorry,
Yeah.
what is the exponent?
Oh, this is c times k. So just think of c as being some constant. Okay. Okay, so why is this such a hard restriction? I mean, clearly clique is a monotone function, right? If I have a subgraph of size k and I keep adding edges, that subgraph is still going to be there. Okay? So, I mean, you might conjecture, reasonably, I think, that if f is monotone, then monotone circuits are optimal. Right? So maybe we don't need the NOT gates at all. So this turns out not to be true. We actually have exponential separations. So the clique is not an example, but there's an example of functions which require exponential size monotone circuits, and but there are small, like polynomial size non-monotone circuits. And if you want an example, instead of looking for a clique in a graph, just look for a large matching. So like a large set of disjoint edges. That'll do it. So this is already telling you that something interesting is going on, right? Okay. However, this is not the end of the story. So this is actually true if you assume f is something called a slice function. Okay, so what do I mean by that? So let me just draw a picture. So rather than give you a really formal definition, I'll just draw some pictures. Okay. So here's a kind of a crude picture of the Boolean cube. I guess it's a diamond. So, I mean, think of it as like organizing all the strings in 0, 1 to the n by Hamming weight. Okay? So down here we have the all 0 string. Up here we're going to have the all 1 string, and then it's divided by Hamming weight layers. Okay? So these are like, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc. Okay? Okay. So a slice function, I mean, a Boolean function is going to give a 0, 1 label to everything in this cube. So what a slice function is going to do, the only place where f is doing anything non-trivial is on one slice. So if you just pick a slice in the cube, and above that slice, the function will be constantly 1. Below that slice, the function will be constantly 0. And on this slice, f of x can just vary however it wants. Does that make sense? So this is clearly a monotone function, right? I mean, as I go up in the cube, I'm only going to flip from 0 to 1 and not from 1 to 0. So for these functions, the non-monotone and the monotone complexity actually coincide up to like a small additive factor. Okay, so this is something that's really nice about monotone circuits, I think, because they give you a method of progression in some sense, right? We have exponential lower bounds for regular monotone circuits. We know that if we could prove the same, use these techniques and somehow modify them to attack these kind of functions, then we could actually get the whole thing. Like we can try and improve the lower bound, the best lower bounds for non-monotone circuits. So let me tell you a little bit about where the techniques break down. Okay? So here's what a slice function looks like, right? So where's the clique? So what does the clique function look like? Well, it's not going to be embedded in a slice. I mean, obviously. You can have, graphs that contain cliques of all different Hamming weights. So in general, it's going to look something like that. So up here, as usual, we'll have inputs of Hamming weight 1. Down here, we'll have inputs of Hamming weight 0. But the boundary between the 0 and the 1s can be very complicated, right? So down here, the inputs of like minimal 1 Hamming weight, right? These are like minimal accepting instances. Let's say f of x is 1, right? This would just correspond to the graph just having a k-clique and nothing else, like a k-clique and a bunch of isolated vertices, right? Whereas up here, we're going to get these 0 instances. And this is going to be graphs which like have edges basically everywhere, but they still avoid having a k-clique via some complicated structure, right? An example of this would be take any graph that you can color with k-1 colors so that all the edges are not monochromatic. If it has a k-clique, it can't have a k-1 coloring, right? But if I throw in all the edges that a k-1 coloring admits, I'll have n-squared edges, basically all of them. Okay? So now, what's amazing is that if you look at this proof technique by Razborov, this one that proves this exponential lower bound, the key is that he proves something much stronger than this. He doesn't actually prove a lower bound for circuits for clique. He proves a lower bound for any monotone circuit that separates these inputs of very low Hamming weight from these inputs of very high Hamming weight. So to say that again, he's going to focus on 2 sets of inputs. So you should think of this one set as being just the set of k-cliques, and the second set as being, say, k-1 colorable graphs. So up here, it always answers no. Down here, it always answers yes. So any circuit that's correct has to output the right answer on both of these. But the key is that in the proof, he really needs these things to be separated by very, very large Hamming weight in order for this to make sense. And if you think about it, these are kind of the hardest instances for a monotone circuit, at least intuitively, to separate, because a monotone circuit can treat inputs, it can handle transitions in inputs going from 0 to 1 very naturally. But here we've kind of inverted it, at least intuitively, right? We have the 1 inputs are very low Hamming weight and the 0 inputs are very high Hamming weight. So if a monotone circuit is like searching for a subset of 1s, right? If it's searching for one of these guys, if I instead feed it one of these guys that has lots of 1s, it has to do a lot of work to try and locate it. That's the very rough intuition for what's going on. Okay? So the moral of the story is that if this gap, which you could think of as like the Hamming weight of the 0 over the Hamming weight of the 1, is large, then we can prove exponential lower bounds. Okay? In your test sets, in your U and your V sets. But for slice functions, we need this gap to be exactly 1. Okay? So now here's a natural question. Can we shrink the gap? actually prove lower bounds where on monotone circuits where we can compress this gap as close to here as possible. So if you look at Razborov's proof, the gap that he gets, maybe this is a bit too small, is basically n squared, right? Maybe a smaller polynomial than n squared. So the k minus 1 colorable graphs will have n squared edges. The k cliques will have k squared edges. So the ratio is like n squared over k squared. And if k is like a small function, maybe it's not k squared, it's like 2 minus epsilon or something like that. Okay? And now we need to get the gap all the way down to 1. So in a recent paper with my PhD advisor, we were able to shrink this gap so in particular, we can prove exponential lower bounds still. The function's no longer clique. It's something quite a bit harder because you have to structure the function quite a bit in order to make this work. The size of this gap between the 0 and the 1 instances, instead of being order n squared, it's actually constant. Some gigantic constant. But in some sense, this makes us a constant factor away from non-monotone lower bounds. Now, there's a small caveat here, which is that we have to assume the circuit is a tree. Okay? That's OK, because I mean, I'm still interested in, I mean, a tree-like circuit is a formula, so it's still an interesting question to me. Okay? And there's some other work on this problem. So there's also a work due to Ben Rossman, who proves lower bounds, proves not quite exponential, but still strong lower bounds, n to the log n. He's going to assume the circuit is still a tree, but it's not going to be a constant gap. It'll instead be on the uniform distribution. And this is kind of like a small gap, because if you think about the uniform distribution on the cube, most of the mass is going to be centered around the middle. And like, you know, only with very low probability will you leave the middle. But with some probability, you'll get the all 0 string and the all 1 string, right? So it's not directly comparable, but it's still considered quite strong progress in this direction. So to conclude, what I'd like to work on this year is pretty simple. The first thing is to eliminate this, both here and also over here. I'd like to make this thing smaller. You know, can we make the gap as small as we possibly can? And finally, I'd like to develop more connections between these average case results on monotone complexity and non-monotone, actual pure non-monotone complexity. And that's basically it. Okay, thanks.